So when we talk about kinematics, we're talking about the language of how things move. It's important that you understand most of the vocabulary we have is very, very specific in here. This is not like other classes where the vocabulary can be arbitrary. What I mean by that is a word like distance and displacement sound similar, but are vastly different. Speed is not velocity. The first thing I need to point out is that each one of these words is chosen to convey a meaning so that there is no ambiguity between the things one person says and how the other person interprets their speech. If our goal is to mathematically model motion, we have to be very specific about the language choices we make. So we are always trying to be very careful about using the correct vocabulary. There's several other pieces we have for this, but I'm going to focus on these for just a few minutes. First, displacement is what I would consider it a more important quantity, but displacement and distance are related. Displacement is your absolute change in position. Your absolute change in position. While distance can be answered when answering how far have you gone. These aren't definitions per se, but we're trying to convey the difference. So let's assume that this evening when you go to bed, you will be going to bed in the same place that you woke up this morning. That's pretty likely for most of you. So if that's true for you and your head will hit the same pillow that it rose from this morning, your displacement across the entire day is 0. Because you ended up where you began. Does that really tell you anything about how you went about your day? So displacement has limited information it can give you. Well, most of you probably traveled a couple of miles over the course of the day. Maybe 10, 15, 20,000 steps getting from one place to the other back to your pillow. Distance is like an odometer. It's recording whether you're going forwards or backwards or sideways or up or down. It is constantly increasing. Distance never decreases. If you're always moving, you're always adding distance to your day. But displacement compares the end point with the beginning. It doesn't care about the middle. So, when we compare distance and displacement, we're really looking at two different things. Two very different things. Now, this part's important. Displacement is a vector quantity. Distance is a scalar quantity. I'm not sure you've heard these words before or not. I'm using the word scalar and vector. Who's seen Despicable Me? The first one, the good one. Yeah, because the bad guy in there is named Vector. He's committing crimes with magnitude and direction, because that's what a vector is. A vector is any quantity that includes a size portion and a directional portion. A scalar value only has size. So, I want you to consider the difference here. Distance is a scalar. It doesn't indicate any of the directions you've traveled. It's just how far you've gone. It is just the odometer, like in your car. Displacement is a vector, and that's what's important about its difference. It should not only tell you your change in position, but in what direction you came from. So displacement has both directional information and it has size, which is going to bring me to another word I have to use. This is not a physics word, but It's one of these words that people think is a physics word. And I'm going to ask you on your next test to tell me the magnitude of something. Magnitude can always be replaced with the word size. They are the same word for this class. So the magnitude of your weight is how much you weigh. When we say the word magnitude, we are specifically talking about the size portion of a vector. So if the word magnitude confuses you, use the word size in its place. All right, I'm going to change screens here for a minute. I need to draw something, but I have exactly 1 minute to do so, so I will not be successful. All right, some of you saw this on the graph before. True enough? Labeling it, position here, time here. We were able to talk about the fact that the slope had meaning. And in this case, the slope is the velocity of the object. Now, it's important that we understand why this is a velocity and not a speed. Speed is the magnitude of velocity. So speed is simply how fast you're going. Velocity is speed and in what direction. Now, direction's hard for you guys. Might be one of the hardest things we do. The reason why we use graphs a lot in here is because graphs give us a physical representation of what we are observing in the real world. So when you guys were doing that simple lab of walking in front of the detector, this picture is a display of where you were for every point in time. The thing we discovered about that is we can figure out from that display your velocity. We can acquire other information that was not obvious by looking at the graph of what you did in front of the detector. Now, this is relatively benign. There's not a whole lot here that's interesting, but it does allow us to create something from this. You know from looking at this that there is a relationship that goes along with this. Wouldn't you agree? Meaning you were taught in your math class that y equals mx plus b. I'm not saying something you don't already know, right? But here's what I want you to recognize. Y and X were just placeholders in that class because they had nothing. There was no data. That was a math class. And what we did, these placeholders have meaning for us. The Y was where you were. It was the position, the vertical part of the graph. The horizontal part of the graph was when. And we've already figured out that the slope was the velocity. So this relationship actually told us more. It gave us x as a function of t. This is function notation. You won't have to know that. I just like to say it out loud because it makes me feel smart. X as a function of t, which we find from looking at this equals vt plus b. What do you think b represents here? Yes, ma'am? Right, it's where it intercepts. It's where the object was at time 0. So we have a name for that. We're not going to put b there. Where the object was at time 0 is the initial position. I'm going to use an x with a little I next to it. Is that okay? That's not how I do it in my other class, but that's how they do it on your equation sheet for this class. Yes, sir?
For that is the I in the subscript.
That is an I in the subscript, yes. So I'll call this the initial position. We doing okay so far? Math symbol means final minus initial. 6th and 7th period both got this one. I'm so disappointed. So disappointed. You guys remember the delta? Now, maybe it didn't get taught to you, and it's okay. The delta is a symbol that means change in. Final minus initial is change in position. And based on our discussion yesterday, this is displacement. These represent a discussion of what we call motion equations. The idea or the concept behind a motion equation is to tell us where the object will be at some future point in time. There's an asteroid right now. It is on its way to the Earth. It's going to hit the Earth. Whether it's a global catastrophe or just a falling star, I don't know. But there's somebody out there, not enough people, mind you, but there's somebody out there who's trying to find it. They're trying to look at it, trying to track it, so they can come up with its motion equation. Something that will describe where it's going to be at all future points in time. Because the Earth's motion equation is very well known. We know where the Earth is going to be at all future points in time. We want to compare these two motion equations to see if there's any time where both the Earth and its meteor will be in the same place at the same time. Because that will be a big deal for us. Either because it'll be beautiful to watch, or because we'll need to find a hole in the ground so we can dig in there and stay. Either way, we hope somebody's out there doing that. Motion equations are an attempt to take all the information we know and make predictions about what's going to happen in the future. That's our goal in all of physics, is to make predictions about the future. We believe that if we know enough initial information, we can figure out the future. And I'm talking about boring stuff now, you walking in front of a detector, not particularly interesting. But it also explains all physical phenomena. All of it can be explained by looking at this. Why the electrons in the antenna of your phone shake the way they do. Because of the electric fields in the room coming from the local antennas sending you data. That's a motion equation that explains why they shape the antennas the way they do. Right now you guys have got what, 1 bar in here? Maybe 2 bars of service, if you're lucky. Most of you all are 1 bars in here. And I know it. Doesn't bother me at all. But it means that your phone right now is using battery power as fast as possible. It's got the least amount of signal, so it has to listen harder. And it has to transmit with more power just to get out. If you don't think that's part of what we're talking about here, it seems like a stretch. It's not as far away as you might think. By the way, let's move this forward a little bit. Yeah. A lot of uncomfortable squirming now. I have an idea. I want to see if you guys can maybe work this out for me, because you're all smarty smarts. Most of you way smarter than me. I am but a feeble teacher. Look, I figured out a long time ago this is apparently the best I can do for my life, so I love teaching, actually. This represents 2 different objects. We'll call this one object A and this one object B. And this is a position versus time graph. And right here represents 5 seconds. Okay? Maybe take, it took me 30 seconds to do that. Take 20 and do it yourself. I'm going to ask a series of questions about it. These questions would have been your quiz today. Okay? We were behind. They may be your quiz on Friday. I said I put 2 stars up there because I didn't know if I'd make it as far as I wanted. So it is very likely that something like this might be asked of you in a couple days. Fair enough? All right. So I'm going to ask a question. You might want to write it down and think about the answer. So question number 1. Actually, let me just see if I can move this over to the side a little bit. Question number 1. Let's just say that these 2 guys are racing, A and B. They're racing, bicycle or running or something. When the clock begins, who's ahead? Take a moment, answer it. When the clock begins, when I say go, Who had a head start? I love that noise. All of my videos are going to have that beeping in it. Keep that in mind. He might not be in the right position. Must reposition at 1 mile every 6 months. That's a pretty slow car. All right, so question number 1. At time 0, who's ahead? Who thinks they have the answer? Yes, ma'am.
Person B would be ahead.
Can you tell me why you think it's person B?
Because at 0 on the time axis, person B has a greater position.
How many of you would agree with that statement? It should be 100% of you. She's right on the money. This person is further along that x-axis at time 0 than the other person. Person A should be mad because they got a head start. So, question 1, the answer is person B is ahead. So, let's consider question 2. Question 2 is, I think, more interesting. Who's ahead at 7 seconds? Think about it. Who's ahead at 7 seconds? That's adequate and sufficient time. You should write the question down. So I'll be nice. I'm not going to pull any more of these little thingies. I'm going to let you guys answer of your own volition. But who believes they have the answer to this? A couple people? A lot of people. All right. Let's go all the way in the back. Rudy, what do you got?
I said A.
You said A is ahead at 7. I don't see 7 seconds. How do you know where to even look?
I looked at the line, and I looked at 5 seconds. And since at 5 seconds, I assumed that they're equal. Since A continues on, I said that it was ahead.
Hey, Rudy, I'm going to ask you a follow-up question. Is there ever a point after 5 seconds where B is ahead?
No.
No. So it really doesn't matter where 7 seconds is, as long as I know it's on the other side of the 5-second mark, right? Yeah. So here's my harder question. Think about it hard, because I'm going to hit you on this one. Who's traveling fastest at 3 seconds? Who's traveling fastest at 3 seconds? All right. Got a few seconds to think about it. Who thinks they have an answer? Yes, sir, in the back.
At 3 seconds, A is traveling faster.
How many of you agree that A is traveling faster? Sure. Slope is steeper. Good job. Who's traveling fastest at 5 seconds? Think about it. Yes, sir? How do you know? Now, this is an important question. The 5-second mark, there's a group of you in the room who think they have the same speed because the graphs cross there. But that's not about speed, is it? The point where they cross happens to be position. What is actually happening at the 5-second mark? Who can give me a 1-sentence explanation? All the way in the back. Yes, sir.
Person A is overtaking person B.
Perfect. That's what's happening at 5 seconds. Person A is overtaking person B. All right. Was that hard? Not too bad? All right. So if I ask a set of questions like that on Friday, no difficulty? All right, we'll see. Because you might realize that that's not exactly the level I want you to work at. Can I show you more of the level I'd like you to work at? And so we're going to take a look. Before I do this too much, does it make a difference if I were to add in person, let's say person C? Does that make it much harder? How is person C different? What is expressly different about person C? All in back on the left. What you got? My left. Your right.
Person C has a negative slope.
And can you interpret what that means?
He's slowing down.
He is not slowing down. but I think that's what about half the classroom thinks. Yes, ma'am.
Does it mean that he's like going the opposite track as them?
Yeah, he's going the opposite direction. That's right. Yeah. A and B are traveling away from the origin. Person C is traveling towards the origin. That's the only difference. All right, so we feel comfortable with this information. Now, I would like you to write a one-sentence description of what's happening in this picture. If you need another sentence, that's fine, but I think you can do it in one. A one-sentence description. Maybe read it to the person next to you, too. Bounce it off them before I call you out. This time, I'm calling two people out to read their sentences. I've got my two volunteers. I'm looking at the 2-second, 5-second, or 7-second. Where do they quite possibly have the same speed? Raise your hand if they have the same speed at the 2-second mark. The 5-second mark. The 7-second mark. All right, very few of you voted. But if I want to look at a place where they have the same speed, I'm looking for where a tangent line at one of these points would have the same slope as A. So if I label this point 1, point 2, 3, 4, 5, and 6, consider tangent lines for each of those. You guys do know what a tangent line is, right? So where would a tangent line at one of these points be about the same slope as A? Is there any chance it's over by 1 or 2? Any chance it's over by 5 or 6? No, it's got to be 3 or 4, right? It's got to be the only place where a tangent line would have maybe the same slope. So I'm trying to make a line that has the same slope. Would you say 4 is pretty close? I think it's pretty close. So that's about where I think they have the same speed. Now, at that point, at that moment, B was still behind A. But it was at that moment where he started to catch up, where the distance between them got smaller and smaller. It was at 7 seconds where he passed him. Right? So basically, person B was just kind of, sitting there. Person A took off, and he tried to catch up. And he eventually did. Questions about this? Yes, sir.
So yesterday you said the difference between speed and velocity is scalar quantity and velocity is a vector quantity, right?
Mm-hmm.
Okay. I was just making sure that my notes were right.
Your notes are right. All right, so all right, I'm going to begin now. I'm going to make an assumption, and it might not be the correct one, that most of you have not dealt with a velocity versus time graph. And normally I would start off with a graph that's a little different than this, but I want to jump right in with this. This is a velocity versus time graph. It is demonstrating how fast the object was going and in what direction. This does not tell me where the object is. It does tell me how fast the object was traveling. It also tells me the direction the object was traveling, because you'll notice that this graph has both a positive side and a negative side. We're going to assume today that this is all talking about one-dimensional motion. One-dimensional motion. Which means that direction is either forwards or backwards, up or down, left or right. Does everybody understand what I mean by that? It's like you're traveling on a number line. So, the first thing I want you to think about is, what's this object doing? I would really talk it out with the people around you. Make sure you feel comfortable before I kind of hit you up in class.